It's yours now.
Thank you. Thanks for the invitation and the occasion to speak here. It's really a great pleasure. Just to say a word about when I've met Rafail. In fact, he came to visit the Technion where I was at the time in the mid-90s. And this was very shortly after I had completed joint work with Ildar Ibragimov, which was completely by correspondence, and I had never met him. And in those days, of course, you could not just open a Zoom session and blabber yourself to death. You had to really exchange letters. So for many years, I kept a handwritten manuscript that Ildar sent me that eventually became part or the bulk of our joint paper. So when Rafail came, I was wondering what, I mean, he did not visit me, but we started chatting, and I was kind of surprised on how enthusiastic he was about anything, and he immediately suggested something we should think about, and this is how we had a collaboration, and I guess this is the reason why I'm speaking here. So I'm mentioning all that because from this exchange, I understood that Rafail would always like some piece of math that not necessarily is exactly what he was doing, and he would be curious. So since I'm not doing statistics and certainly not these days, I thought I'll tell a story about random walks that we can all relate to. So the story, so I hope, Rafail, that you will enjoy that, and if not, it's not very long. So that's the worst that can happen. So I'm going to talk about one-dimensional random walk in random environment. So the first half of my talk is going to discuss some old results and some background, but all the new results I'm going to talk about are joint work with Darcy Camargo, who was a postdoc at Weizmann, and Yuri Kiefer, that I'm sure many of you know. So let me start by describing the model. So we start with an environment. So what is an environment? We have a collection of, I like to think of them coins, omega I, which take values in a compact subset of the open interval 0, 1. So, I want to exclude the possibility that they get arbitrarily close to 0 or arbitrarily close to 1. That's not very important, but it's just technically convenient. This is an assumption referred to as uniformly elliptic in the literature. So these omega i's are going to be, at least in the beginning, IID. So at each site of Z, you have an omega I like that. That I refer to as the environment. Whoops, sorry. Something bad happened. So this is what I refer to as the environment. And on this environment, we start a random walk. So what does a random walk do? For convenience, let's agree that it starts at 0. And then when it visits site I, it jumps to the right with probability omega I. Okay? So of course, this model includes classical random walk the classical random walk model. In the classical random walk model, these omega i's are just constant. So the underlying measure is just a Dirac at some p0. And in that case, classical theorems of probability theory tell us that there is a law of large numbers. Xn over n converges to a constant, which is non-zero as soon as p0 is not 1/2. We have a central limit theorem. We have large deviation principles through the theorem of Cramer, etc., etc. So this is a model. Now, two things to say about the model. First, terminology. So there are several measures floating around. This will play a role. One is a measure conditioned on the environment, which I denote by P omega, and I call it a quenched measure, borrowing from the physics literature. And under this measure, Xn is just a reversible birth-death chain, but non-homogeneous, spatially non-homogeneous. Okay? So it's a Markov chain, so that's good. On the other hand, one of the difficulties is, of course, that it's not space homogeneous, so many tools cannot be applied. On the other hand, if I look at the big space, at the annealed space, which is where I average over both the environment and the random walk, what I get myself is a process that is spatially translation invariant. Okay. However, it's not Markov anymore, because if by observing the location of the walk, I learn something about the environment. Okay. So this model was introduced in the early 70s. And one of the first results is a theorem of Solomon. So let me describe it. So remember that rho I is simply 1 minus omega I over omega I. So in the deterministic case, rho I equal 1 is just omega I equal 1/2. So that's kind of the borderline between drift to the right and drift to the left. So the theorem is that the process is transient if the expectation of log of rho is non-zero. And if that expectation is negative, the process is transient to plus infinity. So these two things are not very hard to convince yourself. They just come from the reversibility of the model, so you can easily compute the probability to hit, I don't know, plus L before hitting -1, write it in terms of the environment and analyze it using the reversibility of the model. So from now on, I'm going to, or at least in the theorem, I'm going to assume this case, that the expectation of log rho 0 is negative, so the process is transient to plus infinity. There is a certain quantity that you can introduce that will play an important role. So I introduce it, called S, which is related to the distribution of these variables omega I. It's just the largest R such that the expectation of rho 0 to the R is less or equal to 1. Under the uniform ellipticity condition, this is a well-defined quantity. It's neither infinity nor 0. And under this assumption, xn over n converges to a velocity. But unlike the classical random walk, this velocity may be 0 even if the process is transient. So this is the first hint that something interesting may happen here. And what this means is that there exists transient random walk in random environment with 0, which are not ballistic, with 0 velocity. Okay. And this is essentially due to trapping effects. So to explain that, imagine that I draw an arrow with a direction according to whether omega 0 is larger than 1/2, which is drift to the right. Sorry, omega I is larger than 1/2, which is drift to the right. And omega I is smaller than 1/2, which is drift to the left. So on Z, I have this configuration of arrows that maybe look something like that. And once in a while, I may have pockets, large pockets, which look like this. So when the particle reaches this point, it may get stuck for a relatively long time. And the parameter S is measuring the strength of these traps. The smaller S is, the larger these traps can be. And these traps are the reason why you may have transients, but with zero speed, okay? And in fact, this parameter S determines completely the behavior of the RWRE. So in particular, when S is larger than 2, you have central limit theorems, both under the quenched measure and under the annealed measure with different centerings. When S is between 0 and 2, the scaling of the fluctuations depend on S. You get some stable limits. This was done in particular by Kesten, Kozlov, Spitzer in the mid-70s in the annealed setup. And then almost 20, actually more than 20 years later, 30 years later, there was a renewed interest in this kind of questions, and the emphasis moved to quenched results. So I'm not going to discuss these results, I just mentioned that as background. I should say that for S smaller than 1, the displacement is much smaller than N. In particular, the displacement is N to the S for S less than 1 in the transient case when S is smaller than 1. And there is one interesting case that I will return to at the very end, which is S equals 0. This is the extreme case of strong trapping effects. This happens in particular if the distribution is symmetric, the distribution of the environment is symmetric with respect to reflection. So the probability to see a certain omega I and to see its reflection is the same. And that's a case that was put forward by Sinai in the mid-80s with the surprising result that the walk is much more confined than you would expect. In particular, the displacement is of order log n squared. So much, much smaller than in the other regimes. Okay, so and this is a case of recurrence. Okay, so the walk is recurrent, but the scale is certainly not the central limit scale. It's a much smaller scale. So Sinai proved this result, and then Kesten and Golosov identified explicitly the limit distribution. Okay, so that's the background on random walk in random environment. One later piece of work had to do with tail estimates. For me, the important part are large deviation principles because they will play a role in the continuation of the story. So let me tell you about those. Suppose that I look at Tn, which is the first heating time of location n. So I start my random walk at 0. This is location n. My random walk goes back and forth, does all sorts of things. And the first time it gets to n, I call it Tn. And now by the Markov property, I see that the exponential moment of Tn can be decomposed into a product because Tn is a sum of Ti, where Ti is just the heating time, sum of Ti minus 1. So, and each time you can apply the Markov property. So you see that the expectation, quenched expectation, given the environment of the exponential of lambda Tn decomposes into an ergodic product. By ergodic product, I mean that each of the factors has the same law, but it's in a shifted environment. And because of that, when you compute the limit of that, almost surely it gives you a certain deterministic quantity, which I call lambda. And it's from this point, it's not a very hard exercise in large deviations to show that Tn, the heating time of n, satisfies a large deviation principle with rate function, which is exactly, so it's a quenched large deviation principle, which is just the rate function is just the Legendre transform of that lambda that came from the ergodic theorem. Okay? And from that, it's not a very hard step to show that the position itself satisfies a large deviation principle with a rate function related to the previous one. And this is the reason I'm showing you all that, if I work annealed, namely I allow also averaging over the environment, At the level of large deviation, at the level of 0-1 laws, annealed and quenched are the same by Fubini's theorem. But at the level of large deviation, things are very different. And in fact, there is a large deviation principle where the rate function is a sum of two quantities. First, there's an entropy term, and then this function h is an entropy function. And then there's a quenched rate function, the same rate function we discussed before, but in a new environment. And the intuition is rather clear. When you're talking annealed, what you can do is change the environment to a new law. This is my eta. This has an exponential cost, which is measured by the entropy. And in the new environment, you can apply a quench type results. Note that it requires you to have that this eta is ergodic, in fact. I wrote stationary, but in fact it should be ergodic, because you want to be able to apply the law of large numbers for the quenched result. Okay? So the moral of all this story is that you can have a large deviation principle for the position and for certain heating times. And when you move from quenched to annealed, an entropy term will show up. Okay? So this is rather old work, now 20 years old work in joint work with Kometz and Gantert. Major development occurred later related to high dimensions, where there are many results, but even more questions. High dimensional case, there are many fascinating questions, but I'm not going to discuss them at all today. Okay, one word about the rate function. So I said that there is a large deviation principle, which means that the exponential rate of decay of probabilities is governed by a certain rate function. And this is a shape of the rate function. So for s larger than 1, when the velocity is strictly positive, this is how it will look. There will be a annealed rate function, there will be a quenched rate functions, and they will not be the same. Okay? And in general, the annealed rate function is lower because annealed probabilities are larger. It's easier to do annealed large deviations because you're allowed to change the environment, which in the quenched situation, you're not allowed to do. Okay. So that was part one. Part two is a completely different thing, seemingly different thing, which is the Erdos-Renyi-Shep limit theorem. I'm giving here not the most general form, but the forms that will be easy to compare later with what is coming. So suppose that I have xi IID random variables, and suppose that I decide on a block length k of n, which is logarithmic. K of n divided by log n converges to n. Then, if I look at increments of my partial sums or of a random walk based on it, I look at increments normalized by the length of the block. So this is a slope, if you want, a local slope at scale log n. I can ask about the maximum slope. And the answer is completely given in terms of the Cramer rate function for the random walk. So in terms of the large deviations for the random walk. So in particular, the answer is that this maximum, so essentially the maximum over blocks of size a log n, is some constant, deterministic constant, as n goes to infinity, times log n, and the constant is just given by this form. And the idea of the proof is relatively simple. So let me give you the heuristics that I'm sure many of you know. You divide the interval 0n to blocks of size k of n. And you note that the increment on such blocks are independent. So you have essentially independent Bernoulli trials. And you ask, what is the maximum of independent Bernoulli trials? Of course, this is not quite right because you also have blocks of this form that you consider in that theorem, but it turns out to capture the correct behavior. And the important thing is that what happens here and what happens here in terms of time is completely independent. So the temporal independent increment of the walk allow you to deduce this limit. So the beginning of the results I'm going to present is to ask, okay, what happens for random walk in random environment? And surprisingly, this is a question that was not discussed before, at least to my knowledge or to our knowledge. And in fact, Yuri asked me this question, and in the beginning I thought it would be trivial, and it turns out to be slightly more complicated than that. So here is a theorem. So exactly the same situation. Up to here, or even up to here, it looks exactly the same. Namely, you take blocks of size A log n, you look at a random walk in random environment with S larger than 1, and you ask what is a maximal increment normalized by the length of the block. And the answer is that there exists a deterministic constant that you converge to, and that constant is given by some I star of x. But now things get a little bit more complicated. So this I star of x, you would think it's a rate function, but in fact, despite our efforts, we could not really represent it as a rate function. It's a function. We know some of its properties. It looks very much like the rate function I showed you before. So if you go back here to this rate function, if you go back to this rate function here, so remember that's an entropy plus a quenched rate function. So here also you obtain an entropy plus a function in a new environment. But this IF is not quite a rate function. And it's certainly not explicit, but it's not quite a rate function. It is obtained by taking certain limits, which we prove converge, on a collection of rate functions. And those rate functions have to do with the rate function of heating times, but in a transformed environment. Okay, so that's the result. I would like to make a few remarks on the proofs. I of course am not planning at all to give you any details on the proof. I have no time on that, but I want to say a couple of words on that. So the first thing is that it's not very hard to show that almost surely when S is larger than 1 and you are ballistic, the maximal backtracking you are going to do is going to be some constant log n. So log n is kind of the natural scale. And in fact, spatially, you can divide the space to blocks of size C log n. And essentially what happens in different blocks is completely independent because there is no backtracking. However, in one such spatial block, the random walk can go back and forth, can attempt many times to cross this block fast. So there is a competition, an unnatural competition. On the one hand, on the original environment, the walk has a tendency to go right. You're trying to make it go faster, so it doesn't seem reasonable to try to make it come back and try again and again and again in the same block. So for such situations, you would expect that the idea of independence, as in the classical case, would work. However, remember that there are traps. Even when S is larger than 1, there are traps, which means that there are atypical blocks in which somehow the drift is towards the left, not towards the right. So the walk is transienting to the right, but the drift is towards the left. And then you may make many attempts in the same block. So the maximum of these attempts may be larger than the typical value for one attempt. And there's a competition between these factors. And the function I showed you is kind of capturing this competition, taking into account how frequent it is to see atypical blocks. This is measured by the entropy. Okay, so this is just in a word on the. Now, there are several natural questions on this. There are, in the classical case, there are functional versions. We did not discuss that at all. Probably for S larger than 1, one could deduce it from our work, but this is not done. More interesting is a case where S is between 0 and 1, namely walk, which is not ballistic. In that case, more returns are possible, and this effect that I told you about becomes more pronounced. And in particular, for technical reasons I'm not going to get into, our approach fails. So one has to do something different, and I do not venture an answer there. And of course, if you go to S equals 0, which is a Sinai setup, this brings a different scale. Okay, so that's the result. If I have 5 more minutes, I would like to, do I have 5 more minutes?
Yes, for sure.
Yes, okay. So, I would like to advertise a completely different problem. So since I know that Rafail likes problems, so here is a problem for you for your birthday. Okay? Actually, it's not my problem. It's a problem that is advertised by Itai Benjamini, which I think is very nice and very puzzling. So let's take an environment like in Sinai's walk. Namely, we have, so I repeat the setup, we have at each location a coin Wi. So this is I, this is I plus 1, etc. And as in Sinai model, let's assume that the distribution of omega I is, the annealed distribution of omega I is invariant under flip, which means that omega I and 1 minus omega I have the same annealed law. Okay, have the same law. Now, the difference, the twist is that when you are at location I, omega I decides the direction you're going to jump to, but not the magnitude. And the magnitude is going to have heavy tails. So this is an example. Okay? So again, I'm describing what happens. You reach location I, you flip the coin. If the coin omega I turned out to be to the right, you don't go one step to the right, you make a jump. And that jump has a certain distribution, in particular with heavy polynomial tails. Finite second moment, but tail of the order 1 over k to the 4 for them. That's a particular case that has been simulated. And now the question I would like to ask is, what is the range of the walk? How far does the walk get? So, of course, the maximal, because at each step you have a chance to make a jump which is large, you can easily compute what is the largest jump. And the largest jump turns out with this scaling to be n to the power 1/3. So question, is the displacement n to the 1/3? Is it larger? Is it smaller? If you start to, some simulations suggest that the limit is 1/3, but I should tell you immediately that simulations are extremely unreliable in trying to get an exponent of this type. So that's a widely open question. I don't know the answer, and I thought it would be a nice place to stop. So thank you for your attention.
Thank you very much for your talk. So we start some questions now. You can write it on the chat window.
Sorry, one small question. Xn is more than n and 1/3 with what probabilities?
Almost one.
Almost
So,
one.
so what I mean by that, okay, this is very colloquial. I mean that the probability that Xn star is larger than n to the 1/3 minus delta goes to 1 as n goes to infinity. That's immediate because of the maximal jump business.
Thank you.
Thank you. Is there any other questions? If not, I have one very naive question, which is a more statistical one. Is there any work? It is interesting to estimate parameter on the random environment with the observation of the trajectory of the random walks, or
Yes. So that's an excellent question. And in fact, I was going to say that I'm not going to talk about statistics at all, but there are statistical questions, and I forgot to say that. So thank you for reminding me. So in fact, Francis Comets and collaborators have looked into such questions. And in particular, you see, if you look at the trajectory of the walk, it will get stuck. And we know quantitatively for how long in traps. So, so in fact, you will be able to kind of reverse engineer the Erdős-Rényi law. Namely, once it gets stuck for a long period in some pocket, this tells you something about the environment, and in particular about this parameter S. Okay. So of course you cannot. I don't know. It depends on what exactly you observe, and things are different for the transient and recurrent cases. But you can get quite a bit of information. And as I said, Francis and collaborators have looked quite a bit into this question.
Okay. Thank you very much. So I want to thank all the speakers of this first session. Thank you again for being here. And I will leave now the chairman of the second session, Oleg, will start the new session. Thank you very much.
Okay, thank you.